between 200 and 270 miles. From here, the ISS looks down on the planet. At this altitude, the environment is instantly lethal. The extremely low pressure would cause a person's body fluids to vaporize in seconds, while the little air that remains can reach temperatures of more than 2,000 degrees Fahrenheit. There are also dangers of radiation exposure in this forbidding atmosphere. But safely aboard the ISS, an international team of astronauts lives and works. Including on this mission, Satoshi Furukawa, a native of Yokohama, Japan. An ardent baseball fan, he takes advantage of zero gravity to play a solo game. A medical doctor, one of Furukawa's jobs on the station is to study the effects of microgravity on the human body. He often conducts research as both doctor and patient. He's also the mission photographer. Using an extremely sensitive high-definition camera, Furukawa will capture nighttime images of Earth's upper atmosphere. The ISS is an ideal platform to study the edge of space, thanks to the cupola observation window. It offers a priceless view of space and the planet below. Its heavy shutters open to reveal windows for photography and viewing. It's from here that Furukawa will aim his camera when the station's orbit takes it into the Earth's shadow, which it passes into about every 90 minutes as it orbits the planet. Designed to capture never-before-seen phenomena, it's so sensitive that it can shoot color images in near total darkness, bringing to light places once hidden by the blackness of space. He's hoping to capture images of an elusive and mysterious form of high-altitude lightning, only recently discovered and still little understood. The story of these strange lights in the sky began one night in 1973, when a U.S. Air Force pilot named Ronald Williams was surprised by an unusual sight.
There was a typhoon over the South China Sea. I happened to be flying over the typhoon. And as I was going right towards the center of the typhoon, there was a big thunderstorm just off the center of the typhoon. All of a sudden, just by accident, I was watching it, because if I'd have been doing anything else, I wouldn't have saw it.
Williams saw a bolt of lightning go straight up from the top of the clouds.
When it came up, I happened to be watching it, and I just watched it go up. I reported it, and nobody had believed me. They said lightning don't go straight up. Has a discharge on something.
But it turned out that Williams was not the only pilot to see lightning emerge from the top of a cloud and shoot upward towards space. As sightings accumulated, they became a part of aviation folklore, rare and unconfirmed events that hovered just outside the boundaries of real science. Until another chance sighting provided more evidence.
A fellow by the name of Jack Winkler had some detectors out. He was looking for something else, but he discovered them by accident with equipment that was operated on dark nights in Minnesota.
While testing a low-light video camera in 1989, Jack Winkler and a team at the University of Minnesota accidentally captured a black and white image that seemed to show the elusive upward lightning the pilots had described. Fittingly, this ethereal phenomenon became known as a sprite, a whimsical name that captures its fleeting nature. These giant pillars of light sparked an intensified interest in lightning and the dangers it presents to spacecraft during launch or landing. Today, astronaut Satoshi Furukawa is looking for thunderstorms, sprites are only found where lightning is present. But spotting sprites isn't easy. They only accompany bolts of lightning over 10 times more powerful than normal lightning. In 10 minutes, it will be nightfall again. So Furukawa quickly prepares his camera.
Recorder power is on. Monitor is on too.
This specialized camera should be able to capture images of the elusive sprites, even in these low-light conditions. He'll need this extra sensitivity to catch a sprite. If any sprites appear, they'll be above powerful bursts of lightning. Across the world, over 2,000 lightning bolts flash every minute, and over 20 million strike the US each year. They're 4 to 5 times hotter than the surface of the sun. And the most potent can discharge up to 1 billion volts of electricity. Unlike the superheated lightning flashing below the storm clouds, the sprites above are huge, but electrically much weaker and faster, disappearing on average in less than 70 milliseconds. Furukawa maintains his vigil for several hours, but without much luck.
It's difficult.
His camera recorded a huge number of lightning flashes, but no sprites appeared above them.
I felt like a hunter. It was impossible to predict where it would appear.
Though the search is frustrating and difficult, he's determined to capture a sprite. In part, because of a letter he received during training for his ISS flight. The letter was from an Israeli lightning expert, Yoav Yair, who wrote to inquire about the mission. He enclosed a photo of Ilan Ramon, Israel's first astronaut and a crew member of the ill-fated Columbia mission. Ramon had brought with him a high-sensitivity black and white camera to try to capture images of sprites from space.
And it's a big day for the Israeli science community.
Ramon's partner in the research was Professor Yoav Yair.
I asked him, please bring me one sprite image. He said, don't worry, I'll get you a couple.
After capturing over 9 hours of thunderstorm footage on board, he succeeded and transmitted several images of sprites back down to Earth. But tragically, Columbia never made it home. It disintegrated upon re-entry. Though debris was scattered widely, the camera that Ramon had used to capture sprite images somehow survived, with some of Ramon's work intact. One image of active lightning over Central Africa shows a bright flash of light above the lightning and arcing up towards space. It was a sprite. Ramon captured images like this one from several vantage points in orbit. Yair and his research team studied these photos and were surprised to discover how frequently sprite events occurred over large tropical storms and how widely distributed they were. But there was still much to learn. Yair saw Furukawa's mission as a great opportunity to advance the understanding of sprites.
It's so touching. I can feel their passion. I was there at their scheduled landing spot and looking up the sky. The Columbia never came back. They were my friends and my colleagues. I was very sad to lose them. At first, it was difficult to get back on track. I didn't feel like doing anything. Then I thought, we must take over their work and move forward. I thought that was the survivor's duty. So I am honored and happy that I was given this chance in this way.
So nearly 250 miles above Earth, Furukawa is working hard to further Ramon's legacy. He readies his camera as the flight path takes him towards Europe and into the nighttime darkness, Earth's shadow. He won't have much time. At ISS speeds, traveling over Paris to Rome takes just 2 minutes. Looking down, he sees the lights rimming the boot-shaped peninsula of Italy. In 10 minutes, he'll be over Central Africa. Weather patterns and topography make this the world's most lightning-prone region. Because it's estimated that only 1 in 10,000 lightning bolts produces a sprite, Africa's very active skies make it one of the best places to spot one of these elusive events. So the first step in capturing a sprite is to track the kind of extraordinary monster thunderstorms that produce superbolts of lightning. And figuring out where they might be is Yoav Yair's job.
Okay.
He analyzes weather patterns on the ground and sends the locations of potential sprite-producing thunderclouds to Furukawa on the space station.
This is a very exciting and emotional thing for me to do because it reminds me of the things that we did for Ilan Ramon and the crew of the Columbia in 2003.
With Yair guiding him, Furukawa circles the globe looking for the kind of monster thunderclouds that could produce a sprite. Then, while flying over the Middle East,
Incredible!
he sees something. It's clearly a sprite flashing over the thundercloud and surging towards space. And it looks like a color version of the one captured by Ilan Ramon from the Columbia Space Shuttle. It's the first clear, high-definition color photograph of a sprite taken from above. And there are more. Ahead is Taiwan, Japan, and mainland China. A giant sprite appears over Beijing, near the horizon. The white flash below is an unusually powerful bolt of lightning. The sprite above is far off. It may not look especially large, but some sprites can be almost 40 miles in height, dozens of times taller than ground-striking lightning bolts. Altogether, Furukawa captured 6 sprites.
It was a real surprise to me. It's so exciting when something previously invisible to us finally starts to become visible.
The footage was sent to Yoav Yair and an international team of sprite researchers who are continuing the work of Ilan Ramon and the lost Columbia crew.
Oh, that's very nice. Great.
Now it's much more detailed, better camera, color. We only had black and white, but it was really exciting for me. Actually, it really moved my heart to see it. I have to imagine this because they are all not with us, they're all gone. But I'm sure that if he knew that their mission was accomplished 8 years later, and maybe even going on later, they would feel fulfilled. He would be proud, I think.
Images like these are helping scientists to understand how a huge storm can generate sprites. During a thunderstorm, electric charge builds up in a thundercloud, causing lightning to emerge from the lower part of the cloud and strike the Earth, discharging an immense electric current. But if that lightning bolt is powerful enough, It can trigger a sympathetic spark above the cloud.
As you go up in altitude, the density of air decreases. And so low-density air is easier to make a spark in than high-density air. So a sprite is really caused by lightning down in the lower atmosphere that exerts a stress on the upper, thinner atmosphere and causes a spark up there.
And that spark gives rise to a sprite. As the scientists examine the images, there's one that attracts a lot of attention. Captured in one of Furukawa's pictures, the top of one of the sprites seems to reach all the way to the air glow layer. The air glow is part of the ionosphere, which is a vast sea of electrically charged particles, or ions. It's these particles, with help from the sun, that create the glow.
Air glow is due to solar radiation at short wavelengths, ultraviolet wavelengths, UV, the same stuff that sunburns us if we're outside without our sunblock, or X-rays, that we use to image our bones, and that can transfer energy to the molecules in the atmosphere, and that energy transfer causes a glow.
But the most important thing about the air glow may not be why it glows, but where it's located. It's the lowest part of the ionosphere, the uppermost region of the atmosphere. It begins about 60 miles above Earth and extends over 600 miles to the very edge of space. The air glow is just the most visible component of the ionosphere, which is created by radiation from the sun interacting with the topmost layer of Earth's atmosphere. So the image of a sprite reaching the air glow shows the incredible heights these massive sparks can reach. But these stunning images from the space station still leave many questions unanswered. How exactly do sprites form, and what accounts for their peculiar shape? To answer these questions, the group decides to try something that's never been done: to fly closer to sprites and to photograph them simultaneously with 2 different cameras on 2 different airplanes, hoping to combine these images digitally and reveal the anatomy of a sprite. The planes will also be equipped with the same super-sensitive color HD camera Furukawa has been using on the International Space Station. But their real secret weapon is a high-speed black and white camera that shoots 10,000 frames per second under low light conditions. It will be able to show the formation of sprites in slow motion.
It will be the first time that we've had 2 aircraft simultaneously trying to image sprites with high-speed cameras. So it's very exciting for us.
They chose the area where the Great Plains meet the Rocky Mountains as a likely place to hunt for sprites because it's famous for very big nighttime thunderstorms. You can see huge thunderclouds there in the summertime. The weather is sunny almost 70% of the year. The intense sunlight heats the ground and causes a strong upward air current. This, in turn, creates active thunderclouds one after another, producing lightning. But only the biggest lightning flashes of all produce sprites. And once again, it will be Yoav Yair's job to help the team in the air find those huge sprite-producing thunderclouds. He and his team will be at the Yucca Ridge Field Station, a weather observation facility on the Great Plains north of Denver.
Oh, now you got it.
No,
You got it okay.
They will forecast where a sprite might appear and direct the planes.
All right.
At 5 p.m., the flight team gathers to discuss strategy for tonight's mission. They call the control station. Scientist Jeff McHarg, who will be on one of the planes, is asking for the lightning forecast.
We were just looking at the charge moment change map and then the weather map.
But it's not weakening, and the good news is it's moving into some extremely unstable air.
Walt Lyons of the Yucca Ridge Field Station is working with Yair to analyze the weather data. In this satellite image, clouds are shown in blue. That day, thunderclouds were developing in a variety of places. But would they produce powerful enough lightning to produce sprites? Back at the airport, the pilots talk among themselves. Usually, they avoid big storms, but tonight, they'll have to fly in and around the thunderclouds, hunting for the perfect position to capture sprites. They know it will be a rough and difficult flight. As soon as it gets dark, thunder begins to reverberate around the airport. The researchers board the planes on what looks like a promising night. At 9 p.m., the two jets take off. They're heading for thunderclouds 120 miles away that are vigorously producing lightning. The cabin is in constant communication with Yair and Lyons at Yucca Ridge.
Essentially, they want some kind of a central location.
He evaluates the data and gives the pilots the latitude and longitude of large thunderclouds where sprites might appear.
For reference, we'll be on this data collection run for about 10 minutes.
Outside the window, they see a huge thundercloud begin to glow with lightning.
Oh, it's here. Lightning. Quite promising.
Somewhere in the darkness above the cloud, they are hoping a sprite will occur. The high-speed camera is adjusted slightly upwards to shoot the area above the flashing thunderclouds. Jeff McHarg, who has spent 20 years chasing sprites, can barely contain his excitement. But Yair and Walt Lyons on the ground can see an unexpected change in the thundercloud.
They are here, and if they go like this, they would get this part. But
You know, both of them are starting to weaken.
The large thundercloud that was expected to grow has started to split in two. They've been in the air for 5 hours, with no sign of those elusive sprites. And now, the lightning is quickly losing momentum. Despite the promising forecast and their careful preparation, they have no choice but to return to the airport, defeated.
It was horrible. Yeah. I've seen much larger storms, you know, where you get really large sprites that happen pretty often, and this was just too small.
We'll see. Fingers crossed for the next one. Good night. Good night, everybody.
They realize this will not be easy. On the 4th of July, while people all over America are celebrating, the Sprite team hurries to the airport. They've been waiting for the right kind of weather for a week. Finally, new storm clouds powerful enough to generate sprites have appeared.
So if we go like here,
If we don't see lots of sprites, and this starts to get more intense, then I may want to extend up. We should just
go as soon as they get ready, I would say. Yeah.
Both planes take off into a stormy sky. While Denver watches fireworks below, they prep the cameras and get ready.
30 seconds.
They start to see flashes of lightning below. On the ground, Yair and Lyons are trying to figure out the best way to position the planes.
But then they would have to turn down, or do you want them to circumvent it?
Well, can they punch through and come around the other back?
Go all the way and
Up
then
to about 47 degrees and see if they can punch through it.
The two thunderclouds shown in deep blue have collided, and major cloud development has begun.
Yeah, maybe it's like...
They send the coordinates of the strongest lightning to the team in the air.
South of WPRT and new coordinates are WPRT, north 38 degrees, 20 minutes.
Outside, lightning flashes are everywhere. A monster cloud with a diameter of more than 300 miles is releasing electricity with frightening intensity. The scientists rush to position their gear. The frustration and anticipation of the previous week is getting to them, and tension in the cabin is high.
Sprite! Wow! That's a heck of a sprite there. Did you get it?
For an instant, a giant red flash appeared. On replay, they can see beautiful shafts of light thrusting upwards towards space. The mysterious sprite in all its glory. Then, the sprites keep coming. On board, the team reviews the stunning and unique images. This sprite was shaped like a mangrove tree. It's been captured in more detail than any sprite until now. Just like its name, this sprite evokes a fairy with wings.
Yeah, very big jellyfish. It's pretty. Very pretty.
It indeed looks like a jellyfish with many tentacles. Sprites of many different forms appear, one after another. Seen up close, they have a variety of shapes. Eventually, a sprite appears that demands special attention.
This is spectacular.
The umbrella-like top of this sprite reaches an altitude of around 60 miles. That's the altitude of the airglow layer that appeared in Furukawa's footage from the International Space Station. The image confirms that sprites interact with the ionosphere. Now it's time for the high-speed camera. It's designed so that when a sprite is sighted and the button is released, the previous 3 seconds of footage will be saved. This is the momentary flash of a sprite taken by the super-sensitive camera. And when shot by the high-speed camera, it looks like this. In just a few hundredths of a second, countless particles of light rain down. This is the first time a sprite's formation has ever been revealed in such detail. During the night, 14 sprites were captured by the high-speed camera.
8,000, yes, very good.
What else will the footage reveal? With great expectations, they return to the ground.
Not too bad, huh? That's amazing.
It was fabulous. It was amazing. I haven't seen anything like that ever.
The long night is over, but they know their work is just beginning. Back in Denver, the team gathers to make some scientific sense out of their spectacular sprite footage.
The halo above and the elf below, and that's just because it's expanded out in front. Right.
At first glance, this sprite may seem to burst up from the storm clouds towards space. But when seen by the high-speed camera, the movement looks completely different. Bursts of light appear out of the center, spreading both up and down. In fact, when examined in slow motion, it appears that sprite formation is more complicated than early reports had indicated. And what about this sprite shaped like angels' wings? With this one too, bursts of light suddenly appear out of darkness. They go down, and the next moment up, and then down again. They change their direction as they unfold. So what is really happening? Within the sprite, electrons are colliding with charged particles in the atmosphere, creating a pathway for the electrons to travel. Where they go depends on the concentration of electrons and the composition of the atmosphere. Sprites are beautiful and intriguing. But do they actually have a role to play in Earth's upper atmosphere? Yukihiro Takahashi is investigating the aftermath of a sprite. Once the electrons cut open a path, the atmosphere around it becomes highly electrified. Following the sprite's path, a large electric current continues to flow from the thundercloud to the ionosphere, which shows up as the airglow in many sprite images.
The sprite flashes only for an instant, but at the moment when it flashes, a conductive path is created. The electrified path doesn't disappear when the flash ends, but stays there for a while. The effects are thought to last several seconds to minutes.
The result is a massive transfer of electric charge in the space between the cloud and the ionosphere. The team also successfully captured a sprite from different angles, as they had originally planned, using high-speed cameras placed on the two aircraft. By combining the images from the two cameras, the three-dimensional structure of the sprite becomes apparent. A large number of electrons collide with the atmosphere, creating brilliant bursts of light and opening channels where the electrons can flow. Each sprite channel can be hundreds of yards wide. A sprite event is like a switch that turns on an electric current in the space between the Earth and the ionosphere. In fact, our planet is surrounded by electric current, from the surface to the edge of space. Like lightning, sprites help to complete a global circuit, allowing charge to flow continuously around the Earth. But sprites reach much farther than lightning. And unlike lightning, sprites can transfer charge into the ionosphere, to the edge of space. Not only that, but the bolts of lightning that create the sprites are so powerful that they literally reverberate around the world.
When a sprite occurs, the parent lightning that causes the sprite radiates electromagnetic waves. Those waves propagate in what we call the global circuit.
Earl Williams of MIT studies sprites from this remote laboratory in western Rhode Island. Williams and his equipment are nearly off the grid out here, but they're completely plugged into the biggest circuit of all, the global electric circuit.
We've been monitoring this phenomenon for nearly 2 decades at this site, trying to look for long-term trends.
In fact, scientists have actually been measuring the global electric circuit on this unusual site since the 1950s, when the lab was set up by Williams' predecessor, Charles Polk of the University of Rhode Island.
The antenna immediately behind me is Charles Polk's. The more distant antenna is one that we constructed when Polk's antenna was struck by lightning and blew the antenna into many separate fragments all over the meadow we're sitting in right now.
Williams got involved with early sprite research by collaborating with Walt Lyons of the Yucca Ridge Field Station.
Every time Walt saw a sprite in Colorado, which is roughly 2,000 miles from here, we would see a big disturbance here in Rhode Island.
The antenna Williams is using measures a very low-frequency wave, like a steady hum, that resonates between the Earth and the ionosphere.
When a sprite occurs, the lightning that causes the sprite sends waves in that thin cavity around the world 2 or 3 times. And it is exciting something called the Schumann resonances. And the Schumann resonances is a manifestation of what we call the AC global circuit.
Earl's aunt was a prominent violin player, so it's not too surprising that he thinks of it in musical terms.
The vibration of a violin string is very much like what happens with Schumann resonances. We have a fixed string length, and there's one wave on the string which has a fixed frequency, say the A note of 440 hertz. For Schumann resonance, we have a fixed length, but the length wraps itself around the world. And for that fixed length and the speed of light, we have a fixed frequency of 8 cycles per second. So they're both examples of resonances, this one being a mechanical resonance, that one being an electromagnetic resonance, but the same wave phenomena applies.
It's almost like the music of the spheres, or of the Earth at least.
No matter where you are on Earth, if you have an antenna, a vertical antenna, like the one behind me, you will see an oscillation on that antenna at roughly 8 cycles per second. And that is maintained continuously by all the lightning on the planet. Every time there's a lightning flash, a small fraction of the energy in that lightning flash feeds into this global resonance.
The Schumann resonance is present all the time. It never dissipates, because there's always lightning someplace on Earth. And when a sprite is produced by a superbolt of lightning, there is a spike in the Schumann resonance signal.
Every sprite lightning is a bell ringer for the Schumann resonances. One of these giant lightnings will single-handedly excite the whole Schumann cavity with electromagnetic waves. And everyone on Earth who has a receiver in the range of frequency of 8 cycles per second will detect a sprite event. Here on the oscilloscope, we have an example of the Schumann resonance signals. You can see the characteristic 8 cycle per second oscillation continuously. That's called the background Schumann resonances. Occasionally, you'll see a big increase in the amplitudes. Those events are the events that make the sprites. These are the lightning flashes, the very energetic lightning flashes that create sprites in the thin upper atmosphere.
Earl's science may be cutting edge, adding to our understanding of planet Earth. But his equipment is a little bit old school.
Because the Schumann resonances oscillate at only 8 cycles per second, it is kind of a low-tech operation here. I mean, we do digital recording of the signals, but you know, these are very low-frequency signals you can put on an oscilloscope, and you don't need high-bandwidth equipment to record them. But you have to be in a quiet place. You can't do this in the middle of a city. There's too much background noise. And that's why we're out here in this very beautiful site in the middle of nowhere.
And super powerful lightning produces not only sprites, but other weird phenomena as well.
There are actually a whole zoo of creatures up there that are caused by lightning. There's something called an elve, and it's like a pancake of light within the airglow layer, and it's caused by the radiation field from lightning. Then there is a halo, which is also a pancake shape, but at somewhat lower altitude. And then there are blue jets and pixies and a whole host of other optical phenomena that occur in conjunction with lightning flashes.
Since the Schumann resonance fluctuates slightly depending upon factors such as the temperature of the Earth, Williams thinks it's one important way of measuring the health of the whole planet.
It's a natural setup for looking at the entire Earth. You have one quantity which represents the entire planet. And it's hard to dream up another such circumstance. It is like taking the EKG of the planet.
The global electric circuit surrounds everything on Earth and connects us to the edge of space. Sprites feed into the ionosphere from below. But from above, the sun also affects the ionosphere, resulting in the vivid displays of the aurora borealis. Auroras are light displays caused by the collision of charged particles streaming from the sun into our atmosphere. There are two types of auroras. The discrete aurora, like the northern and southern lights, have well-defined boundaries that can be seen with the naked eye, and diffuse auroras that spread out over a wide area and are less colorful. 93 million miles away, auroras are born from a landscape of blistering temperatures and violent eruptions. From the surface of the sun, huge volumes of solar material in the form of charged particles are blasted into space. A fleet of satellites monitors this solar activity. Stereo A and Stereo B satellites are making 3D images of the sun and also tracking solar activity. These eyes in the sky paint a detailed picture of the sun and the powerful forces erupting from its surface. The constant stream of charged particles. The solar wind is so violent it would strip away the Earth's atmosphere if it hit our planet directly.
The sun you can think of as a really big angry hairdryer in a lot of ways. It's constantly blowing hot, energetic wind out in all directions, not just directly towards the Earth, but in all directions. And this hot, energetic, fast-moving particle stream hits straight on with the Earth.
Earth's magnetic field blocks and deflects the solar wind, protecting our planet from a full-on assault. But there is a back door that allows some of the charged particles from the solar wind to reach us. In the Earth's shadow, there is a region in space where charged particles accumulate. These particles, though drastically decreased in number, sneak in through small gaps in Earth's magnetic defenses. The charged particles dash toward Earth and interact with the magnetic field, which deflects and diverts them to the poles. They rain down, forming luminous rings in the sky. The beautiful, vibrant colors of the aurora are visible evidence of the particles' interaction with Earth's second line of defense, the atmosphere.
The aurora are different colors at different altitudes, depending on the gases in the atmosphere that the particles are interacting with. So it's red at higher altitudes, it's oxygen, and then blue and green with oxygen and nitrogen as it gets denser into the atmosphere where the gases get thicker. And then for really, really strong interactions of the particles, energetic particles, really...
Gravity. According to Albert Einstein, gravity is not just the attractive force of planets and suns. It's a warping of space and time, what scientists call space-time, in the presence of massive objects. A planet, for example, goes into orbit when it's caught in the warped space surrounding a star, like a ball spinning around a roulette wheel. With the mass of a star squashed down to a point, a black hole is a deep puncture in space-time.
When a black hole is born, the energy gets transformed from the energy of the matter to the energy of warped space-time. So it's a transformation of the form of the energy from one to another, but the energy is still conserved. What you're left behind with is warped space-time that has a huge amount of energy in it.
With that energy, a black hole can affect its environment in profound ways. On our planet Earth, we know gravity as the force that brings everything down. The impact releases energy, a crash. A thud. A shatter. When matter falls toward a black hole, the energy released can reach astronomical proportions.
When we look at how they affect the rest of the universe, we look at what happens around them, what happens when stuff exploits this huge gravitational potential, this huge gravitational hole that they form, and how that is exploited to make energy.
Such energy emissions are part of a growing body of evidence that black holes, famous for hiding in the dark, have a history of outbursts that have reached across the cosmos and shaped the universe we know. Scientists are following this energy like a trail of clues, leading ever closer to the black hole's dark heart. Astronomers once saw black holes as rare and exotic in a universe seemingly dominated by stars and galaxies. A radically new view has emerged from surveys of galaxies and black holes stretching deep into the universe. Giant black holes lurk in the dust lanes and swirling gas clouds at the centers of nearly every large galaxy. What's more, the larger the galaxy, the larger the black hole. That's a clue that they must have evolved hand in hand, each shaping the life story of the other. To find out the role black holes played in the evolution of the universe, astronomers are trying to recreate this shared history with what amounts to a whole new branch of science. They are using supercomputers to simulate the sweep of cosmic history, including that of galaxies like our own. This simulation takes us back to just a few 100 million years after the beginning of the universe. Gravity drew vast pockets of gas into dense centers. They grew hotter and hotter, igniting to become the first generation of stars. These stars lived hot and fast, and in only a few million years, some blew up in powerful supernovae. From these stars likely came the first generation of black holes. Cosmologist Tiziana Di Matteo is part of a wider effort to see what marked these early black holes left on the universe. Her computer program simulates the action of gravity on gas, the formation of stars, galaxies, and black holes. Her goal is to create a virtual universe that evolves like the real one did, with black holes and galaxies emerging and growing together. Our Milky Way galaxy is located in a quiet part of the universe, with relatively few other galaxies around it. Move out across the cosmic void, 50 million light years away, and you encounter the Great Virgo cluster, filled with thousands of galaxies. Recent telescope surveys show that this region is part of a larger pattern of galaxies resembling a vast spider's web. To get her virtual universe to look like this, Tiziana needs to know what cosmic conditions gave rise to black holes and galaxies in the first place.
So it's a beautiful problem because we start from extremely well-specified initial conditions. We know the initial condition of the universe, and that's very rare in astrophysics, in cosmology, in any branch of physics.
Details of what the universe was like in its earliest times have come courtesy of a breakthrough observatory called WMAP. It found a blotchy pattern in a kind of radiation generated soon after the Big Bang. Astronomers believe this pattern is the origin of the spider's web structure they see in their telescopes. It defines the beginning point of Tiziana's simulation. She sets her virtual universe in motion. It covers a region in the shape of a cube over 100 million light years on a side. The result, an intricate cosmic web with gravity drawing matter into filaments and knots on the largest of scales. In places where filaments come together, galaxies and black holes first begin to appear.
All the matter that is coming in from the large scale will also allow the black hole to grow because of these gases being transported from large scale all the way into the galaxy, and the galaxy all the way into the center, and therefore feeding and growing these central black holes at a very high rate.
In this sequence drawn from her simulation, the circles indicate the appearance of black holes within the data. What she finds is that as these black holes gain mass, gravity pulls them toward the densest regions, where a few grow larger than all the rest. How did these chosen few black holes grow so rapidly? The orbiting Chandra X-ray Observatory recently turned up evidence at the centers of galaxies back in the time of the early universe. These images show its remarkable find, actual supermassive black hole pairs, beginning what astronomers believe is a dance of death. In most cases, their forward momentum simply causes them to go into orbit around each other, like a planet around a sun. This orbit can go on for billions of years. To grow large, one black hole must draw the other in, close enough to swallow it. Albert Einstein showed how they do it. He predicted that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. It's like a rock hitting a pond. Some of the energy of the impact is transferred to waves that move outward along the surface. Likewise, a titanic collision of black holes would send waves, gravity waves, racing across the universe.
So you have two tornadoes embedded in a third larger tornado, and they're going to come crashing together, and you want to know what happens when these tornadoes are not made from whirling air, but made from whirling warped space and time.
This simulation shows what happens. As two black holes get close, they turn space into a turbulent sea of gravity waves. These waves have the effect of carrying energy away from the orbit itself. That allows the pair to draw each other in and merge into one.
We go back to half of the age of the universe, and all of these black holes are swallowing large amounts of gas. So it's a fun time. It's sort of the golden age for the growth of most black holes. The reason why is because most of the large major mergers are occurring in the universe around this time.
This simulation shows how a galaxy like our own might have taken shape in a flurry of mergers and collisions. In the beginning, gravity drew patches of stars and gas together. A new, larger patch drew still others. In fact, the universe is littered with galaxies in the process of ripping each other apart and crashing together. In the turmoil of each new merger, another victim is thrust into the jaws of a growing black hole. And in the densest regions of the universe, a small percentage of these monsters have been able to grow to a level of size and ferocity we can scarcely imagine. And yet, amid all the violence, are clues to how the universe, and even places like Earth, came to be what they are. Astronomers have long puzzled over a class of ultra-bright beacons of light from the distant universe called quasars. In time, they link them to the outpouring of energy from the centers of galaxies and to growing black holes. But how can something that emits no light shine so brightly?
2 minutes.
The chance to solve this mystery has drawn a crowd near NASA's Kennedy Space Center in Florida.
80 seconds. Ranges go.
45 seconds.
Mounted in the nose of a rocket just up the beach is the next generation cosmic explorer.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go.
0. Liftoff. The Delta rocket carrying in blast. Gamma ray telescope searching.
The Fermi Gamma Ray Space Telescope is part of a larger effort to explore the role black holes play in shaping the universe.
Farewell. On the other side, yeah.
To me, the idea that we're standing here on this planet in our own little area of our galaxy, we're able to look around and make meaningful measurements, have a theoretical understanding of the entire universe in which we live, to me is something that all of humankind can justifiably take pride in.
The black holes that interest Steve Ritz, a project scientist, and his team are among the largest ones out there. The energy they emit is thought to stem from periods of rapid growth at the center of galactic feeding frenzies. Billions of years ago, in places where the universe was dense with matter, gravity drew swarms of young galaxies hurtling toward each other. A large galaxy grew in the center, and when another galaxy fell toward it, it hurled matter at a central black hole. Force-fed like this, the black hole could grow up to several billion times the size of our own sun. Probing the Perseus Galaxy cluster, the Chandra X-ray Observatory found immense hot cavities hollowed out of the surrounding gas. The culprit, they believe, is a jet of radiation coming from a large central galaxy. As it roared out, this jet created shock waves so powerful it pushed huge volumes of gas beyond the central region. And without this gas, new stars can't form. That explains why some of the largest galaxies are filled with old stars, most likely born before their black holes began erupting. At the same time, a black hole jet can seed the surrounding regions with the heavy elements needed to form solar systems and planets like ours.
The black hole also has the property that as it spins on its axis, as the Earth spins, it drags space into a whirling motion like the air in a tornado, faster near the horizon, slower farther away, just as the air in a tornado is whirling faster near the core than it is farther away.
In the eye of this cosmic tornado, gas and stars flow into the hole along a rapidly spinning disk. The spinning motion generates magnetic fields that twist around as matter swirls in. These fields channel some of the inflowing matter out into a pair of high-energy jets.
So we can extract then the rotational energy of a black hole. Nature can extract it. And the amount of energy you can get out is enormously larger than all the energy you can get from burning all the nuclear fuel inside of stars.
It's the equations of Albert Einstein that describe the source of this incredible power, the extreme warping of space just outside the black hole. What we can learn from these equations doesn't stop at the event horizon. They can also let us enter, with our minds, the realm within a black hole. Most likely, we'll never directly see how those equations play out and live to tell. A future explorer prospecting for data would tempt fate by traveling too close. If the monster is a collapsed star, weighing a few times the mass of the sun, its gravity rises sharply. The pull on the starship's nose is so much greater than on its tail that gravity rips it to shreds. Ironically, you'd find a gentler ride into a supermassive black hole. Its larger size means its gravity is more spread out. What you'd find if you made it inside is the most extreme destination in all the universe. Andrew Hamilton, an astrophysics professor, has been investigating what happens when matter falls inside a black hole. Using Einstein's equations, he and other scientists believe that falling into a black hole is equivalent to moving down a river and tumbling over a waterfall. Like a cosmic precipice, the outermost region of the black hole, the event horizon, is where space itself flows relentlessly in.
What does one mean by space falling or doing anything? It's just that if you put objects in space, then they will move in certain ways. And if you put objects near a black hole, as they approach the horizon, inevitably they must approach the speed of light in order to stay at rest. Otherwise, they're going to fall inside the horizon.
If the black hole is spinning, the central region is bounded by what's known as the inner horizon. In a case defined only by Einstein's equations, an object may whip around so fast it gets flung outward.
If there's nothing inside the black hole except the space-time structure itself, or there's nothing inconsistent about having space fall inside, turn back around and come back out again, because space has no substance, so there's no problem with it moving through itself.
It would be like a river racing over the falls, hitting the rocks below, then flowing back up.
In the strange world of general relativity, you've fallen through a region, a black hole region, where space was falling faster than light. And now space has turned around and is now pushing you outward faster than light.
Imagine charting a starship's course into this topsy-turvy realm. If you survived the fall down to the event horizon, you'd accelerate through it.
You go with the flow, you hit the speed of light at the horizon. Now, you can still see stuff from the outside world, even when you're inside the horizon, but people can't see you because space is falling faster than light.
To understand the chaotic region within, Hamilton has enlisted Einstein's equations in a project to visualize the black hole's inner anatomy. You could only get this close on a spaceship propelled by pure mathematics. Passing through the event horizon, we approach the central zone. As we whip around, we are flung out of a kind of cosmic tunnel known as a wormhole. At its end, we pass through what's known as a white hole. Like characters in a science fiction story, we exit into another time or place, perhaps another universe. This strange passage is the work of theory. In reality, it couldn't form amid all the turbulence.
The moment you introduce any real matter, then the stuff that's trying to fall in tends to collide with the stuff that's coming back out again. There's a turbulent, chaotic maelstrom deep down inside the black hole.
In a waterfall, this collision zone is where water crashes on the rocks and ricochets into the downward flow. Here, turbulence rises. All order disappears. In a black hole, the collision zone is the inner horizon, where swirling matter envelops the central core. That's the end of the line for a starship. It gets instantly vaporized.
The chief characteristic of this region near the inner horizon is that streams of energy are passing through each other, and they're passing through each other very rapidly. That counterstreaming of material begins to build up to the point where it self-gravitates, and that gravity accelerates those streams even faster through each other.
In the gentle world we know, the energy released by gravity quickly dissipates. Whatever crashes down settles into a state of rest. Inside a black hole, the energy does not dissipate. Instead, it builds on itself, rising to an extreme state known as the Planck density. To grasp what that is, imagine taking all the matter we can see with our telescopes, all the trillions upon trillions of stars that make up all the galaxies in the universe, and crush it
down to the size of a marble. No, don't stop there. Keep going. Crush it all the way down to less than the size of an atom. That is a Planck density. And that's the kind of density that is produced inside a black hole. It's the most extreme place in our universe outside the Big Bang.
In this state, temperatures rise to 1 trillion times hotter than the center of our sun. It would be hard to imagine what destructive impact the release of this energy would have. Fortunately, extreme gravity holds it tight within the black hole's event horizon. As astronomers project the continued evolution of our galaxy, they ask, will the matter and energy impounded within its central black hole remain there forever? Or is the black hole, like all other cosmic bodies, somehow subject to the ravages of time? We live at a time in which most of the energy of the universe is produced by stars. Trillions of years from now, all across the universe, stars begin to use up their fuel and fade away. The largest stars fall toward the centers of galaxies, where they're swallowed by supermassive black holes. As the universe decays, it gives way to a long era dominated by the remnants of dying stars and black holes.
The far future of the universe is one where the stars have burnt out and formed neutron stars or white dwarfs and some black holes, and eventually, over long periods of time, the black holes merge together to form bigger black holes.
In time, much of the matter within galaxies will fall into these black holes, and they will become the last bastions of our universe. How long will they last? The answer may come from a theory proposed by the cosmologist Stephen Hawking.
Stephen Hawking applied quantum physics to black holes and predicted that they wouldn't be black but would glow with heat radiation in a very distinctive way. And of course, if there's heat coming off, heat energy coming off, this energy has to come from somewhere.
The energy, Hawking said, would come from tiny particles emerging from the vacuum of space just outside the event horizon. Some of those particles radiate away, taking minute amounts of mass from the black hole, like water evaporating from the ocean. Over time, the radiation grows stronger and stronger as the black hole shrinks and finally explodes. When the last black hole dies, that's the end of the universe as we know it. How can we know if the theory is right and they actually do decay?
If black holes were made in the Big Bang with a mass of about that of Mount Everest, these black holes ought to be going pop about now, and radio astronomers have looked to see if they can see a sort of electromagnetic pulse associated with that. They haven't found any.
There might be other ways to see a black hole decay. From all across space, black hole jets are blasting particles out at very near the speed of light. These particles, called cosmic rays, slam into our Earth's atmosphere with enough energy to create miniature black holes. These mini monsters would decay immediately in a shower of particles, but they are very difficult to observe.
We're almost to store. The emittances look good.
Okay.
What if you could produce collisions this powerful in an Earth-bound lab and under controlled conditions actually create a black hole?
All right, so let's go ahead and
If you
fill.
could then watch it decay, it would provide a unique window onto the future of black holes.
Okay, filling blue.
We'll start collimating in blue ring.
It's hoped that taking two very high-energy small pieces of a very fast proton and colliding them with each other, you can put enough energy into a small enough space that you can actually create the conditions by which a black hole would form. These black holes are